The electromagnetic spectrum has fascinated me for almost as long as I can remember. Every part of it has its own uses and whole fields of study devoted to it. Recently, I've been learning as much as I can about some of the longest wavelengths, including radio and microwave frequencies. We've explored many of the uses of these frequencies in previous videos. For example, because these frequencies can easily be sent extremely long distances, they have obvious applications in data transfer. We've used this property to receive images from weather satellites as they pass overhead. The satellites are hundreds of kilometers away, and yet the image comes in nice and clear. We'll be using this property more in the future to send and receive signals to and from a variety of sources. In another video, we explored how we can use radio waves in a similar way to visible light, and built a telescope that could see in radio frequencies. In the image that the telescope took, you can see the ring of satellites in geosynchronous orbit over 35,000 kilometers away. It looks especially cool when shown in proportion to the Earth. However, in both of those videos, the signals we were looking for were comparatively quite strong. What if we wanted to listen for signals that are weaker, maybe from smaller satellites or objects outside of the solar system? For that, we'll need a much more sensitive system. Such a system isn't that complex, but it has more pieces. In this video, we're going to be talking about two things. The first is a little bit of electrical engineering and how to make custom PCBs quickly and easily at home. The second will be the construction of the first piece of our upgraded radio system. So let's jump right in. First, we need a design for a circuit that we want to etch. I quickly made mine in SketchUp based on a paper that I've linked in the description. Here I've got some test designs on regular printer paper to see how the design came out. We'll be using a special photoresist to mark our designs onto the PCB boards that we'll be etching. For that to work, we need a negative mask. This means that any material that you want to get etched away should be covered so that no light touches the photoresist. Exposure to light hardens the resist and will protect that part of the board. To make our masks, normally we would use clear transparency film, but that stuff is expensive and only works with laser printers, so I thought I'd try to use a material that's a little more readily available and will work with any kind of printer. Here I've got some regular vellum tracing paper. Print out your mask onto the vellum and let it dry. Vellum doesn't absorb ink well, so this might take a few minutes, and be careful not to touch it or you'll smudge the ink. To make sure that vellum works as a mask material, I got myself a package of sun paper. The paper's been treated with a mixture of ammonium citrate and potassium ferrocyanide, and is very sensitive to UV light. The paper comes in black plastic to protect it from light until it's ready for use. We'll be making a sandwich with the paper underneath, the mask on top, and a piece of clear acrylic on top of that to hold everything together. To allow us to transport this sandwich, we'll also need a strong and flat backing material. I'm just using a piece of particle board, but thick cardboard or other wood works as well. Assemble the layers, making sure to line everything up so that there's no edges hanging out. To protect everything from light until we're ready to expose it, we place a large opaque object on top. I found a book works really well for this. Now we can head outside and get ready for the exposure. Pick a spot outside that's sunny and away from shadows. Place everything on the ground or on a table, and when you're ready, lift off the book in one fluid motion. For sun paper, it'll take 3 to 5 minutes to fully expose. When the timer's up, again, in one fluid motion, cover the stack back up. Then we can take everything back inside. So that only our image is saved on the paper, we need to stop the reaction and develop our image. In this case, that's as simple as running water over it. This will wash away any of the unexposed chemical and leave only the material that's been exposed to light behind. Run it under water for 2 to 3 minutes and then gently dry it off with some paper towel. Then we just hang it up to completely dry. Already it's obvious that the vellum is working wonderfully as a mask, and all of our lines are clear and crisp. So that means we can move on to the actual PCBs. Before we can add photoresist to the board, we're going to need to prepare the surface. First, we scrub it down with a scouring pad until the whole thing is nice and shiny. Before we go further, it's best to put on a pair of nitrile gloves. This will help prevent oils from getting on the board and interfering with the photoresist. Then we wipe the whole thing down with acetone to remove any contaminants. The photoresist comes as a roll of dry film and can be bought online very cheaply. It's photosensitive, so work quickly when it's not wrapped up. Take the roll out of the protective wrapping and cut a piece big enough to cover your board. Then carefully wrap the film back up in its black plastic cover. The film itself is actually 3 layers. There's the photosensitive layer in the middle and a protective layer on either side. We need to remove one of the protective layers so that it'll stick to the PCB. To do this, we get 2 pieces of clear tape and place one on either side of the film. By gently pulling, one of the protective layers should come off. Remove the second piece of tape and then carefully place the film on the PCB. making sure not to trap any air bubbles. To make the connection permanent, we'll use a heat gun to gently warm the film. Then we use a paper towel to smooth out the surface and remove any remaining bubbles. You could also use a laminator for this, but a heat gun works fine if you're careful. With that done, we can get ready to expose the PCB. We'll be using the same method as before and making a sandwich of PCB, mask, and then acrylic on top of our sturdy backing. Again, we'll cover it with a book to shield it with light until we're ready to expose it. Bring the assembly outside and expose it for 2 to 5 minutes. As the material is exposed to light, the film will turn a dark purple color. When that's done, cover back up and bring it back inside. After the exposure, the board needs to be developed to remove any of the film that wasn't exposed. This is done using a solution of sodium carbonate. Use a mixture of 1 gram of sodium carbonate to every 100 milliliters of water. I found that cheap Tupperware containers work great for trays for the various solutions that we'll be using in the development and etching process. Before we can place the PCB in the developer solution, we need to remove the second protective layer from the film. Again, use a piece of tape for this. With that done, we can drop the PCB into the developer and gently rub the unexposed film until it comes off as a goopy mess. When that's done, you should be left with just our pattern and bare, shiny copper. Make sure to do a good job with this, or your lines won't come out cleanly. When it's done, we can quickly rinse in clean water, and then we can move on to the etching step. If there are any small errors, you can touch them up using a regular permanent marker. You can also use the marker to draw on any areas that you'd also like to protect from the etchant. In fact, you can skip the whole photoresist step and just draw on your pattern if it's simple and doesn't require very specific dimensions. To etch away the exposed copper, we'll be using a solution of ferric chloride. I bought mine as a pre-made solution, which makes this easy. I poured out about 100 milliliters into a new container, and then dropped the board into the solution. Gently rock the tray back and forth to allow fresh solution to pass over the PCB. After 20 minutes of this, all that should remain is the pattern, and the rest should be bare fiberglass. Take the PCB out, and again, rinse it in clean water. And now, the final step. We need to remove the remaining photoresist so that we can solder to our new copper pattern. This is done with a weak sodium hydroxide solution. Use 1.5 grams per 100 milliliters of water. Unlike the developer step, the darkened photoresist is much harder to remove, so you'll need to use a scouring pad to actually get it off. Once the board is clean and all the resist is gone, we can rinse off the board and we're done. So what is it that we just made? Well, for our radio projects, we need a filter that will remove any of the signals above and below the frequencies that we're interested in. This is called a bandpass filter because it only lets a certain band of frequencies through. This is kind of like putting a gel filter in front of a light. Only the color you want gets through. This particular style of filter is either called a microstrip filter or a hairpin filter. Each one of the hairpins acts sort of like a tuning fork. They only resonate with very specific frequencies. We can tune them by changing the lengths of the legs of each hairpin. The shorter the legs, the higher the frequency that it'll resonate with. We can also adjust the width of the passband by adjusting how far apart each individual hairpin is. This particular filter was made so that the center frequency of the passband was around 1400 MHz. As I mentioned earlier, I've put a link in the description to a paper that I based all of this on, and it gives several recipes for filters for a wide range of frequencies. To wire up our filter, we add a coax connector to either side and attach the center wire to the resonator. The ground, or the outside of the coax, can simply be connected together. As an experiment, I also tried leaving the back on one of the PCBs, so that it was easier to connect the grounds together, but this actually made the filter way worse. This is because the front and back of the PCB started to act like a capacitor in the circuit, which screwed with the filter. To get around this, I simply added a second trace on the top of the board to allow the grounds to be connected without acting like a capacitor. So, let's see if this filter works. First, I set up my SDR and tuned into the radio broadcast frequencies. These should be at least partially removed by our filter if it's working. For the first test, I used just the SDR with no filter. As expected, the signal comes in nice and clear. Now if I repeat that without changing any of the settings, but place the filter in line with the antenna, we can see that the signal is significantly reduced. This filter isn't perfect though, so I'll continue to experiment with the design. Once I've zeroed in the filter to the specifications I want, it and filters like it will be important parts of future projects. This specific filter will be used in the construction of a hydrogen line radio telescope I'm working on. The signal from the hydrogen line is pretty weak, so removing all the extra noise will help a lot in detecting it. A similar filter for a slightly higher frequency will be used for receiving images from GOES and other geosynchronous satellites for many of the same reasons. So be sure to check back every other Monday for all of that. And with that, it's time to wrap up this video. If you've enjoyed, be sure to subscribe and consider clicking the bell to get email updates when I post new videos. In the comments below, let me know what other circuits I should try and make. Many of the projects I'm working on now have come from the awesome comments you all leave on my videos. As always, a big thanks to all of my patrons who continue to help make these videos possible. That's all for now, and I'll see you next time.